Alright, hello, welcome to our first lesson of Unit 5 for Try 2. We're diving into exponential functions. So really quick, I just want to give you some insight into why exponentials are super important. Exponentials are really great when it comes to applying them to real world. They really are useful in so many different scenarios. So like on the technology standpoint, like measuring the amount of people like accessing internet, and how many people are on the internet can be modeled with an exponential graph. This graph specifically right here is for the number of cell phone users between these 2 years. Obviously this now has like skyrocketed and it's probably like way up here now because this ended in 1995. So technology purposes, other reasons we use exponential functions are like microorganisms and bacteria. So if you like biology and learning about those kinds of things, exponential growth is huge. The spread of a virus, COVID, was modeled with exponential functions. Human population, when we look at the population growth within our country or in the world, we use exponential functions. High profits, what we call compounding interest. So that's all about like investing and making that money. That would be examples of some exponential functions. And then last one that I could think of off the top of my head was carbon dating. Because I studied rocks, this was huge. Carbon dating is where you take rocks or fossils and then you look at the element carbon, and you look at how much carbon that object has, and then that can tell you how old the object is. And that's also modeled by an exponential function. So very cool. All of these things apply to exponentials. Now let's like dive into what a key difference is. So linear functions, this is what we've spent talking about a whole like try 1, try 2 were those lines, linear. Something I want us to remember is that linear functions will refer to a set of coordinates that have a constant rate of change. Constant rate of change. Now, what that means, if you don't remember, was a constant slope, or we're constantly adding or subtracting by the same number. So if our y's. Okay. So if we're looking at a table and if our y values are adding or subtracting by the same number over and over again, that also tells us it's linear. Exponential functions, we can see here that we're growing a lot bigger. And what causes this super fast increase is having what we call a constant multiplier. A constant multiplier. So instead of adding or subtracting by something over and over again, what's happening to our y values is that we're multiplying by something over and over and over again. So you can see an example of a graph here. That one looks kind of like a J. Just for future purposes, we call this an exponential growth because that y value is skyrocketing towards the sky and getting really large. So we would say this is an exponential growth. Something is increasing, i.e. the number of people using phones increasing. This would be a growth. Now, another shape for an exponential would be similar to the shape of an L, where we start really steep and then we get flat. And this specific term, again, just for future use, is an exponential decay. Decay, it's decaying away, like when a dead animal decays, right? Their body goes away into the ground, animals eat it, and it eventually just is part of the soil. So decay, we're going to zero. Something that could be good for this would be like, if we have like animals going extinct, that could be with an exponential decay. Again, exponential doesn't have, it's a constant multiplier, not a constant addition or subtraction. Linear, again, adding or subtracting, it wouldn't make sense to say, like, let's say, I don't know, turtles were becoming extinct and dying off. Like, the turtle population isn't like, okay, you 200, sorry, you're gone every single day. The numbers that are dying are changing. The more population we have, the more that are dying, and then as our population gets smaller, less are dying until they eventually die out. So growth, decay. Non-examples would be, well, our lines that we've studied. So that would be a linear function. And then one that you'll learn next year looks like this. Or you could flip it around and make it look like a U. That word is quadratic. So that's for next year. But again, today we're just focusing on exponential and linear. The goal for today is for you to be able to look at a table and tell me whether this is an exponential table, whether it's a linear table, or whether it's neither. And I want you to be able to tell me why, and then tell me what is my y's being multiplied by if it is exponential. Because like I said, exponential means it has a constant multiplier. So I'm going to go ahead and just show you these two examples here. So this is probably the most important thing we're going to talk about here for the next 6 minutes, maybe not even. So these top two are examples of an exponential table. So these are where we're going to find that constant multiplier. So like I said, that means our y values are being multiplied by something each time. So if we look, as we go from 1/2 to 2, what do I multiply 1/2 by to get 1? And the answer is 2. So 2 would be my multiplier. Now we want to check the whole table and make sure it's constant all the way down, because if it's not throughout the whole table, we can't say it's exponential. It has to be a constant multiplier, the same all the way through. So we're going to check the next two and see if those are also being multiplied by 2. How do I get from 1 to 2? Well, 1 times 2 is 2. So that's also times 2. And then 2 times 2 also gives us 4. So for this specific table, we would say, my multiplier is 2. And this is an exponential table because it has that constant multiplier. So again, you're asking yourself, well, what times what gives me that? And if you're stuck, like this one starts with a fraction, so that can be kind of hard to say, well, 1/2 times what gives me 1? So start in the middle and then work backwards. 1 times what gives me 2? 1 times 2 gives me 2. Okay, now I'm going to check multiplication again. Can I multiply by that same number to get 4? 2 times 2. Yeah, does give me 4. And then you can plug that last one into the calculator if you need to. So pick 2 easier numbers, see what you have to multiply by to get your next value, and then check the other ones and see if you can multiply by that same number to get there. Okay, so let's look at this one. Actually, before I move on, this one right here would be an example of that exponential growth. So this specific table would be an example of this graph, where our numbers are increasing and shooting towards the sky because my numbers are getting bigger and bigger and bigger. So this one is growth. This one is slightly different. If you look down as we go down, my numbers are getting smaller. So this one is an example of a decay graph, a decay table. When we see our numbers getting smaller, they're approaching 0, which is like our decay. So So find your multiplier for a decay. Well, because we're getting smaller, that means our multiplier has to be less than 1. In order to get bigger, it needs to be greater than 1. So right away, because I notice these numbers are getting smaller, that tells me that my number is going to be a fraction that I'm multiplying by. And then to figure out what goes in that denominator, just try going backwards, because trying to think of what fraction you multiply 3 by to get 1 can be pretty tricky. So step 1, if you notice your y is getting smaller, know that your multiplier is a fraction. So put a 1, and then to find the denominator, just check backwards. 1 times what gives me 3? 1 times 3 is 3. So that should be my multiplier. And if we check all the way down, 1 times a third is indeed a third. And then a third times a third does give me 1/9. So my multiplier for this one would be 1/3. So those are two of our examples. So these again are two exponential tables. Find a y value to start with, see what you multiply by to get that number, and then check the other ones around it and see if it has the same multiplier. If you see your numbers are getting smaller, know that it's a fraction, and then to figure out the number that goes on bottom, again, just go backwards. 1 times what is 3? 1 times 3 is 3. That's your denominator. Now, non-examples of exponential, so this would be like linear or neither, maybe like that quadratic one that I mentioned, like this one. So what's important to remember is that linear functions, again, have a constant slope, meaning that we're constantly adding or subtracting by the same things. So if you look at this one, I'm going to start off by actually thinking of it like if I were to say, is this exponential or linear? So right away, because we're talking about exponential, I'm going to see if it is exponential. So I'm going to check for a multiplier. 0 times what is 2? Nothing. 0 times anything is 0. So right away, that can't have a constant multiplier. But what I do notice is that every time we're going down, we're adding 2. So if you notice a pattern of adding, or even if it was subtracting, even if it was like subtracting 2, this would be a linear function. So if we see the addition or subtraction taking place linear. And then finally, let's look at this one right away. Let's see, to get from 1 to 0, that's subtracting 1. Oh, but then we're going from 0 to 1, so now we're adding 1. So this one would be neither linear or exponential. So again, if it's easier for you to look at are things being added or subtracted first, do that. If you have a constant thing being added, plus 2, plus 2, plus 2, linear, constant thing being subtracted, linear, and then step it up. If you don't see something being added or subtracted each time, then check for your multiplier. Okay? Well, 1 times what gives me 2? 1 times 2 is 2. Well, now let's try 2 times 2, and that does give me 4. So, that's the key things for today. You being able to tell me whether it's exponential, linear, or neither. And then for those that are exponential, I tell you, I just want to know what is the multiplier. So, again, remember to find the multiplier, you just need to figure out what we're multiplying each y value by to get the next y value. If you notice it's going smaller, it's a fraction. Work backwards to find your denominator. Okay, give it your best shot. You have 10 problems to do, and if you want to do this for extra credit, go ahead. Send me a message when you're done, 3 and 8 are for your mastery.